Here is Intro to Nomenclature.
This concludes Intro to Nomenclature.
First is a confusion that people usually get wrong when it's elements or compounds. Elements are stable atoms that cannot be broken down any further by a chemical reaction, as seen on the periodic table, whereas compounds are two or more elements combined and that can be broken down by a chemical reaction. There are 7 diatomic elements that are not seen in nature by themselves. They have to combine with themselves, where hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all of the 7 diatomic elements. A trick to remember this by is genuine. Gen is the endings for hydrogen, nitrogen, oxygen, and ine is the endings for fluorine, chlorine, bromine, and iodine, and U is for you remembering the whole process. Another thing people get confused on are ionic or covalent bonds. An ionic bond is between a nonmetal and a metal, where a transfer of electrons happen. So one becomes a loser, loses some of their electron, and one becomes a winner, where they gain an electron. So the charges will be formed as the one that loses will become positive and the one that gains becomes negative. Covalent bonds are between two nonmetals. They usually share their electrons equally, canceling each other's charges. A monatomic ion gets their charge from the amount of electrons they will lose or gain. So for example, lithium, which is in column 1, will lose an electron, which is negative, creating an Li plus ion,
This concludes
which is a
Intro to
cation.
Nomenclature.
So a cheat code you can use is by looking at their columns. So column 1 will lose an electron, which makes them a positive ion. Column 2 will lose 2 electrons, which makes them a 2 plus ion. Whereas in column 17, they'll lose an electron, which makes them a negative 1 ion. If it's a cation, you have to add ion at the end of the name, because if you don't, it will just look like an element on the periodic table. For example, lithium will become lithium ion. Anions, you have to drop the ending of the element and add "ide" to the end of it. So then nitrogen, for example, will turn into nitride ion. Now you will learn transitional elements from Chance.
Alright, this is Chance, and I'm going over the rules of transition metal ions. First, you take the name and add the Roman numeral. The Roman numeral represents the charge of the ion. It also includes lead and tin, which are not in the transition metals. The exceptions of the transition metals are silver, cadmium, and zinc. For example, you take copper, you add 3 and put it in parentheses, which equals Cu3+. You also have copper 2 in parentheses equaling Cu2+. Now I will teach you how to do the crisscross method with binary compounds. First, you have the formula name.
Atoms. Atoms. Atoms.
Which is lithium oxide. Then you take the anion name, lithium, and the cation, which would be oxygen. And then you have to take the charge of lithium, or Li plus 1, and O minus 2. And then you combine them to make the formula Li, but you take the charges and you bring them down. So it'd be Li2 and O by itself, because you don't have to write the 1. Now I will be showing you how to get the formula to the name. Okay, so seeing Ca, we know it's calcium. And calcium is an alkaline metal, so we know it has a charge of 2, and we can clarify that because there's a 2 here. So it would be Ca plus 2, and then Br, and there's no charge here, So we already know it's bromide. So it's Br minus 1. And we find the anion name, calcium. We found the cation, bromide. And we combine them, and it's calcium, bromide. And that is the formula to name for binary compounds.
Atoms.
And now I will be teaching you about polyatomic compounds. A polyatomic compound is made up of more than one element. All polyatomic compounds are negative except ammonium, which is NH4 with a positive 1 charge. If it ends in 8, there's one more oxygen than its ite version. And if it starts with hypo, it is one less oxygen than its ite version. And these are the polyatomic ions that are most regularly seen.
I'm Harrison, and we'll be going over hydrates and covalent compounds, such as hydrocarbons and covalent bonds. First, we're going to look at an acid. Naming an acid from a formula is relatively simple. First, we're going to want to look at the anion name. In this example, we have H2SO4. We know that the anion here is sulfate because of the crisscross method that Chance taught us in identifying anions. There are 3 rules to naming an acid. When an anion ends in "ide," it goes to hydroblankic acid. When an anion ends in "ate," it goes to blankic acid. And when an anion ends in "ite," it goes to blank-us acid. So for example, this sulfate ends in "ate." We know now that 8 endings go to blankic acid. So we're going to take the root word of sulfate, which is sulfur, and we're going to do sulfuric acid, and that is the name of H2SO4 in an acid form. Writing a formula from an acid's name is similar. First, we're going to look at the anion suffix. In this example, we have hydrophosphoric acid. Immediately, we can recognize that the root word there is phosphorus. And we know that hydroblankic acid is anions that end in "ide. So we take phosphorus and add that ending, and we get phosphide, which is P with a 3- charge. Next, we're going to want to assemble the compound by equaling out the anion charge with hydrogen atoms, since all acids have hydrogen atoms as their cation. In this example, P has a -3 charge, so it needs 3 hydrogen atoms. Naming a hydrate is also relatively simple. A hydrate is just an ionic compound with water molecules attached to it. So the first step would be identifying ionic components, like the cation and anion. Then what we want to do is match the prefix for number of H2O molecules with the suffix hydrate. Here to the right, we have the prefixes that we will see for hydrates, 1 being mono, 2 being di, 3 being tri, and so on. For this example, we have Na2SO4. Now we know Na is sodium, and we know SO4 is going to be sulfate because of the charges there. So that would be sodium sulfate. Then we have the second component, which is separated by a dot, and there is 10 H2O molecules. So we know 10 by our chart over here to the right is deca. So this would be sodium sulfate decahydrate. Next, we'll be taking a look at covalent compounds. Covalent compounds are just a result of 2 nonmetals sharing a pair of electrons with each other and equaling out to no charge. This includes covalent bonds and hydrocarbons. Covalent bonds are unlike those of ionic bonds, as we explained earlier, because covalent bonds have a ratio of shared electrons that equal out to 0. They do not have a charge. Something that is also unique to covalent bonds are their prefixes. Based on the number of atoms, whether that be polyatomic or monoatomic, they have a different prefix indicating how many are in a specific compound. There are only 2 rules to remember when you're naming elements using these prefixes. If the first element is only 1 in quantity, we do not use mono. The second and third element that are in this compound should end in "ide." For example, here we have CO1S2. This would be carbon instead of monocarbon because it is the first element. And then monoxide because this is the second element and there's only one of them, and then disulfide because there are 2 sulfur atoms. It is also important to remember the prefixes for hydrocarbon compounds. Hydrocarbon compounds, like said in their name, are compounds of specifically hydrogen and carbon. The prefixes that we have in the chart to the right here list the number of carbon atoms. The number of hydrogen atoms are proportionate according to the suffix. If the suffix is "an," the number of hydrogen atoms in a compound would be 2 times that of a carbon atom plus 2. If the suffix was "-ine," the number of hydrogen atoms would be 2 times carbon. If it ended in "-ine," it would also be 2 times carbon, but minus 2. For our first example, we have propane. Now, propane has the suffix "prop," and prop, according to our chart to the right, is 3. So there would be 3 carbon atoms. Now, it ends in "ane," and we know that "an" is proportionate to 2 times the number of carbon plus 2. So we would multiply 3 times 2 and add 2, and that would give us 8 hydrogen. Therefore, propane would be C3H8. This next example, we have octene. Now, oct means 8, so we have 8 carbon. Ene means times 2, so we would have 16 hydrogen. Octene, therefore, would be C8H16. Our last example is pentyne. Pent means 5, so therefore we would have 5 carbon. Ine means 2 times the number of carbon minus 2, so we would take 5 carbon times 2 minus 2, and that would give us 8. That would be the number of hydrogen atoms we have. Therefore, pentene would be C5H8. It is also important to know these prefixes for going in reverse order. For this first example, we have C10H20. We know that 10 carbon atoms means that our prefix will be dec. Now we will examine the number of hydrogen atoms. It looks to be 2 times proportionate to the number of carbon atoms, therefore making this decene. Our next example is C7H12. We know that C7 means that we have 7 carbon atoms, therefore giving us the prefix hept. So that will be the beginning of our compound name. Now when we look at the number of hydrogen, we can see that it's a little bit under 2 times the number of carbon, meaning it has to be ine, because 7 times 2 is 14. Minus 2 would be 12. So this hydrocarbon would be named heptyne. For this last example, we have CH4. Now we have 1 carbon atom, and that will mean we will get the prefix meth. Our number of hydrogen atoms looks to be greater than 2 times that of our carbon atoms. Therefore, it will be ane, because 1 times 2 is 2, plus 2 is 4. So this hydrocarbon is named methane. This concludes Intro to Nomenclature.